I am Alessandro Ribeiro, and you are watching the OpenGLStarter Talks. Today, I'm gonna talk about 3 topics related to 3D character programming: the mesh skinning, the skeletal animation, and the root motion. Before start, I would like to read this biblical text. I heard that this phrase is the Bible summary, so I use it in a lot of places. For this is how God loved the world. He gave His only Son so that everyone who believes in Him may not perish but may have eternal life. Thank you, Eduardo Riggi, for inviting me to the Brazilian computer graphics group that made this study possible. I started to code this framework at the university. Although the name is OpenGLStarter, it has a lot of other functionalities, like math, scene, timer, threads, and etc. The link to the framework is in the video description below. The topics I show here are related with each other. The mesh skin is a technique that allows us to deform a mesh using a simple structure. To control how the mesh skin is applied, we can use the transformation hierarchy and implement our skeletal animation through geometric transformation. And finally, to move our 3D character in the 3D world, we can use the animation as input to do that. Let's start with the mesh skinning. The mesh skinning is a vertex deformation technique. In other words, we will modify each vertex according to some rule. The structure we will use in the transformation hierarchy, it is a graph data structure or a tree. It has a parent-children relationship between the nodes. Because of that relationship, we can assume that the parent transformation affects the children transformation. This is not a new concept in computer graphics, as we use the same structure to model our scene graph. There are some places they call it skeleton, joint, bone, and etc. This is an example of a transformation hierarchy. We have a root, pelvis, spine, and etc. We can associate with each node a local transformation matrix. And to compute the final matrix, we just need to multiply the parent matrix by the children matrix. To compute the final transformation of the pelvis, we need to multiply the root matrix by the pelvic matrix. To compute the final transformation of the spine, 0, 1, we need to multiply its parent matrix to its matrix. The result is the multiplication of the root matrix by the pelvis matrix by the spine 0, 1 matrix. The good thing about modeling the hierarchy this way is that the calculations are straightforward. After calculate all multiplications, we will have 1 matrix per node. Take a look at the matrix representation. We are considering the matrix as a column major. That is, each column is an element of the matrix. Here we have 3 axes and the origin. In this image, we are considering the left-handed coordinated system. When we do a mesh skinning, we need to modify the vertex position by some rule. We use the gradient matrix to do that. How it works? Let's take an example with points and vectors. Imagine we have a point A and B. We can express the vector AB. And once we have the vector AB, we can express B in terms of A and AB. In other words, we can store A in the vector AB and calculate B using the stored values. Now we can do the same analysis, but using matrix instead. We have a transformation A and a transformation B. Now we can express a matrix that's transform A into B. I call this matrix the gradient matrix. The operations are not additions and subtractions, but uses matrix multiplications. The gradient matrix can be calculated multiplying B by the inverse of A. With this definition, we can store the matrix A in the gradient matrix AB. Now the matrix B can be calculated multiplying AB by A. A pose is a state where we have a set of transformations that define a form or a shape. We need a reference starting pose. We call this pose bind pose. The artist can define what we call target pose. A very common bind pose is the T pose. We organize our transformation to look like the letter T with the arms open. Now the artist can adjust the transformation creating the target pose. Let's take a look at the poses together. Each transformation, joint, or bone in this representation is a matrix. Knowing that, we can express the target pose matrix as a modification of the bind pose matrix. Now we can use the gradient matrix expression we saw earlier. When we deal with a mesh data, we have vertex that defines the 3D model form. We have an expression to be applied to this vertex data. For this case, we can think the vertex as a special type of matrix. It is a 1x4 or 4x1 matrix. Let's rewrite this expression. The idea is similar to the matrix multiplication. We need a source point, the gradient that deforms the point, and finally the target point is calculated. How can we define the source point? We can define the same way we did with the bind pose, by positioning the 3D model vertex near the transformation it is related to. If we use directly this equation to modify the vertex position, we're gonna get the same result by transforming a pure scene graph. To get better results, we say the target point is influenced by more than one matrix. The main idea is to create regions of influences per vertex. The 3D modeling tools usually call this rigging or bone painting. Mathematically, we can do a linear combination of the related gradient matrix. Take a look at the equation now. We do the multiplication of the gradient of a joint by its influence, and each vertex can have its own group of transformation influences. This will be a linear combination when the weights sum is 1. If we want to do what is called GPU skinning, we might use the max of 4 influences per vertex. That is, we can send to the GPU the skinning data as a vertex attribute. With this approach, we can define any pose to our vertex data. Take a look at this example. If you want to see the mesh skinning algorithm details, the link is in the video description below. The next topic is the skeletal animation. As we have the mesh skinning working, we need a way to update the vertex position considering the time variation. An animation is any modification of parameters that visually affects an object according to the time variation. Skeletal animation is the animation applied to the transforming hierarchy. To approach the skeletal animation, we need to define what is a frame. A frame is a set of parameters that have been created or calculated to help us define our pose. There are two types of frames: the ones the artist defined and the ones that are approximated, interpolated, or extrapolated. When we talk about parameters, we can think in curves. Each curve can lead to a specific result. We have the linear, hermite, splines, and etc. The artist's tool might have a lot of curves equations. It is common when the tool exports the animation, it comes with a simpler equation setup. We can use this to simplify our implementation. Because of this, we will consider only linear interpolation. In this image, we have the time variation in the x-axis and the y variation in the y-axis. Each keyframe has its own y value. We can store for each keyframe all parameters that compose this state. Note that each keyframe is the parameter set related to a time sample. Now we have the keyframe, our animation system needs to deal with the frames the artist didn't define. The interpolated frames. The images show us the green position are the interpolation frames. But how can we compute them? There are basically two kinds of interpolation, the positional and the rotational. The positional keeps the distance step constant, and the rotational keeps the angle variation constant. There is a link to the video description with the algorithms and equations. When we talk about position interpolation, we think in a vector 3D. We can use the linear interpolation as shown in the left part of the screen. When we talk about rotation interpolation, we think in quaternions. And we can use the SLURP, that is the spherical linear interpolation. Now we can use the plane spherical interpolation as shown in the right part of the screen. The algorithms are different and they give us different results. Now we can see both interpolations overlapped. While the position walk is a straight line, the rotation walk is the arc of the circle. Now we can calculate our interpolation. First, we need to sample the time and discover its amount related to the time of keyframe A and keyframe B. Once we have this value, we can use the LURP for position and SLURP for the rotation. Our last talk in this topic is a comment about the animation transitions. In real applications, you can swap the animations instantly, but it can be more attractive to the user if you have a smooth transition. The transition can be seen as a second level of interpolation. You might think you are playing two animations simultaneously, and you can adjust the amount of the first and second animation you want to present to the user. Take a look at the first line. We need a parameter LRP 0 to 1. Then we need to compute the animation A and the animation B at the same time. The difference here is that we will use the LRP parameter to select the amount of each animation we want to show to the user, using LERP for position and SLURP for rotation. For more information on skeletal animation, you can see the link in the video description. The final topic is the root motion. Now we have our 3D character skinned and animated. We need to move it in the 3D world. When you use the root motion algorithm, you let the artist to define the character's movement. The main advantage of this method is that it avoids parameter adjusting during the character programming. The first attention point is the skeleton organization. We need the definition of a bone that is the root of the hierarchy. Take a look at the beginning of the hierarchy. Here and here. Although the artist can animate all bones, we need him to use the root node to make a movement in the 3D model. The animations can be non-cyclic and cyclic. On both cases, we need to compute the variation or delta between two consecutive frames. Finally, we use this delta to move our character. Let's see the non-cyclic example. Take a look at the image. We need to calculate the vector from the start to the end. The equation is end minus start. Now, the cyclic animation is the complex case. We need to sum the beginning of the timeline with the end of the timeline. Take a look at the equation and the image. For more details, you can see the link in the video description below. Let's see an example of the framework. Now, I'll show you the framework implementation of the skinned mesh, skeletal animation, and root motion at the same time. What this demonstration does: have the CinePalace.cpp, C++, and here we are creating our component, the component skinned mesh. We need to provide to it the 3D model with the vertex painting or the rigging already done in the 3D model, and we need to load each animation by one file, and it's possible to give one name to that animation also. So let's take a look what this load the model base does. Here, basically it loads the model from the file system. Here we need to do a pre-processing step, getting all mesh information that comes from the model, because it can have a scene graph with the mesh positioned in that scene graph. So we need to get all positions and transform that information to a word space. So you get all mesh in local space and process all the information to global space here. The global space is the 3D model global space. This information is not in our scene that we will render. For example, this is the input of our algorithm to process the skinning. Here we process the normals, tangents, and binormals. Compute skinning information. Now we have all positions for each vertex. We need to build our array of vertex influences. This call will do that for us. And this part that I put here, if is GPU skinning, if we are using GPU skinning, I pass some parameters to the shader generator. So I pass the size of the array it will receive with the skinning information. If the model don't fit any of these pre-configured size, it will go to the CPU skinning. Let's take a look at the CPU, what the code does. We pre-process, we upload the data to the GPU here. We have special bits to upload the position, normals, tangents, and binormals, and all other attributes, vertex information will upload as a static data. Now going to skinning on GPU, we set up the array size. Once we do that, we create those arrays. This algorithm basically creates an array of floats, because shader receives just floats, with the bone index, so that we can use this information in the shader we are using. Let's take a look at the shader here. This is the matrix we get. It's an array of matrix. We passed this bone index. I put this plus 0.2 because we are truncating the value to access the array in the shader. So we get the index 1 multiplied by the weight 1, 2, 3, 4. So we reach the limit of our shader processing. After we get this matrix computed, we can calculate the inverse transpose for normal transformations, and we can get the gradient matrix to other multiplications we need to do. And the position, we just get the position from the attribute position of the 3D model multiplied by the matrix with linear interpolation calculated here. Here we have the normal map example also. So we compute the normal, multiplying the matrix we got from the skinning by the normal, and after that we multiply by our visual camera local to word inverse transpose here. This code here is to reorganize the tangent and binormal and pass it to the fragment shader to render the normal map correctly. So back to the component skinned mesh. Once we compute all GPU information, is the skinning index and skin weights, we need just to sync the static data of the 3D model. We don't need the dynamic data here. This is a good thing because we gain a lot of performance doing that. Now back to our skinned mesh load model. Each animation is a file here. When we call load animation, this load animation will add animation using this class. This class is the animation mixer. The interface is very simple. We just need to add a clip. Each call will call this add clip. Once the clip is added to the clip list, we need to call the compute transitions to pre-compute all information we need to make a transition from one clip to another. After that, we just need to call update every frame with the time variation. If we want to change the animation at the runtime, we call play, the name of the new animation, and the blend time we want. And that's it. The root motion, it's a part of the animation system. If I set the callback to the root motion algorithm, each time I call the update, it might call the root motion analyzer. It's an external class to move the character, for example. there is one more thing about the update method of the animation mixer. Each time the update change a node in the model graph, we can see that it calls this onTransform visited with the transform modified. And here we can compute our bone gradient matrix. Here we have already calculated the bone inverse, our bind pose, and we multiply by the target, the bone target, that is this node's current transformation. And this matrix is the matrix that is sent to the shader to rendering when we use the GPU skinning. Let's start it. I got this model from the Mixamo website. The link is in the video description below. Let me show the Mixamo reference model. I got from mixamo.com. There is a lot of animation in this website. I don't know the commercial license, but for personal use, it is free. So I got this model and this animation. This is the walk animation. And the run animation I choose is this one run animation. Look. Note that the animation don't have the transitions. Now we are going back to our demo scene. When I hit the walk button, the character starts to walk. The good thing in use root motion, you can take a look at the foot of the model. It stays at the same place in the ground, with the ground, né? With the ground. It's very cool. Now the transition and the run animation when I hit the shift button. And that's it. This is our mesh skinning, skeletal animation, root motion in one project demonstration. When I was studying all these concepts, I developed a Unity 3D asset. You can find more information on the video description. Thank you for watching.